In today's lesson, we're going to be looking at the format of binary floating point real numbers. Now, you might have had some experience with fixed point notation in year 12. We're going to take a step up from that and see how floating points allow us to represent a greater range of numbers and how we can play around with the accuracy of those numbers as well. We're going to be learning about converting binary floating point real numbers into denary and vice versa. So a bit of maths involved in this particular lesson. So make sure you have something to write things down on, and you should be familiar with how to convert numbers into binary and binary digits into real numbers and vice versa. So as always, let's begin with the prior knowledge check. What is meant by floating point? What is meant by normalization? What is meant by mantissa and exponent? And what do we mean by a binary representation? So do pause the video and think about these questions. Now, floating point to me basically means that the decimal point floats depending on a number of significant digits. And this is normally based on the exponent in some fixed base. In our case, it will be binary or base 2, but you probably have encountered this in scientific notation with base 10. So something like 5 times 10 to the power of 2, that's what we're talking about. Now, how is it different from fixed point? Well, fixed point allocates a number of bits to perhaps the real part and a number of bits to the fractional part. So, for example, if you got 8 bits, you might just say, well, okay, the first 5 bits are going to be the real part, that's the integer value, and the last 3 bits are going to be the fractional part, that's on the other side of the binary point, which kind of looks like the decimal point. Now, the floating point works a bit more differently. The binary point floats, and we'll talk about this a bit later. So what about normalization? Well, this is not the normalization that's part of databases in year 12. That's something different, though the concept is similar. Normalization basically means the process of making something a bit more normal, a bit more standardized. And that's all we're going to be looking at. So when we're using floating point representation, we might have all different types of binary combinations, but there's only one specific set that we call a normalized combination, and that's something that we're going to be talking about later as well. So normalization is just the process of making something more normal, more regular, more standard. So what about mantissa and exponent? Well, the mantissa in mathematics basically holds the main digits, and the exponents define where the decimal point should be placed. So remember that floating point where the decimal point can float, that depends on the exponent. So mantissa holds the actual value, and exponent is where do we place the decimal point. And depending on where we place the decimal point, the value's accuracy and range can change. So we're going to be looking at that as well. So mantissa holds the main digits, and exponents define where the decimal point should be placed. And finally, what does it mean by a binary representation? Well, that's pretty straightforward. Representing real-world numbers as binary numbers. So you're representing something in base 2. The focus for today is to describe the format of binary floating point real numbers. So we're going to be looking at what these floating point numbers mean and how does a computer use them and how do we convert them from one form to another. So let's begin with real numbers. A real number is one with a fractional part. An integer, on the other hand, does not have a fractional part. When we write down a value for a real number in the denary system, we have a choice. We can use a simple representation or we can use an exponential notation, sometimes referred to as the scientific notation. Now, in the latter case, we have options. For example, the number 25.3 might alternatively be written as 0.253 times 10 to the power of 2, or 2.53 times 10 to the power of 1, or 25.3 times 10 to the power of 0, or 253 times 10 to the power of minus 1. All of these equate to the same number. But depending on how we write them, you can see what's happening to the mantissa part, which is the front 0.253, 2.53, 25.3, 253, and what's happening to the exponent 2, 1, 0, and minus 1. Depending on how it's decreasing, the decimal point moves. So in this case, it's moving towards the right, really. And keep this in mind because this will be very useful when we solve questions later on. In floating point representation, if you have a positive exponent, you can move the binary point towards the right, and when you have a negative exponent, it moves towards the left. That technique is very useful in converting numbers between one form and the other. And we'll get to that a bit later. Now, what's the difference between floating point and fixed point representations? Well, a binary code must be used for storing a real number in a computer system because computers only understand two particular values. So one possibility is to use a fixed point representation, and that's what we have been using so far since year 12. In this option, an overall number of bits is chosen with a defined number of bits for the whole number part and the remainder for the fractional part, like give 5 for the integer part and 3 for the fractional part in an 8-bit system. So that's pretty straightforward. Now we also expand on this a bit more, and you probably have seen something like this, where real numbers in 8 bits, normally we allocate the first bit for the sign, then we give 5 bits for the integer part, and now we give 2 bits for the decimal or the fractional part, because the total number of bits allocated must be 8. Now what happens is that in an 8-bit system, you can get 256 values. But using this type of system means we are now limited to the amount of values we can store. For example, using this case, the largest positive value would be 0, 1, 1, 1, 1, 1, 1, 1. Now that's the equivalent of denary 31.75 because 0 is the sign bit, so that tells you it's a positive number. 1, 1, 1, 1, 1 equates to 31, and the last 2 bits equate to 75. Why 75? Well, because we're not going in tenths and hundreds, because that's obviously in the real world, in denary system. In a binary system, we're going to be going up as half, quarters, eighth. So a half plus a fourth equates to 0.5 plus 0.25, which is equal to 0.75, which is the fractional part. So you now have 31.75, and it's a positive number. Try it with the next one, the smallest positive value. So we've got 0, 0, 0, 0, 0, 0, 0, 1. Now in this case, 0, the first 0 is the sign bit. The integer part is all 0, so that's 0. And the fractional part is half, which is 0. There's no value there, so there's nothing. So we only got a quarter. So quarter is 0.25. So that is the smallest possible positive value in this type of system. Now, what about negative values? Now, because we're using this complex way of representing real numbers, we can also have negative numbers in the same 8-bit system. So in this case, the smallest magnitude negative value would be 1, all zeros, and then 0, 1 for the fractional part, which is the equivalent of minus 0.25. And similarly, if you equate the largest magnitude negative value, the first part denotes the sign. So 1 means it's a negative value. 1, 1, 1, 1, 1, we already know means 31. And 1, 1 towards the end means it's half plus a quarter, which is 0.5 plus 0.25, which is equal to 0.75. So it becomes negative 31.75. Now, in this 8-bit system, we still have 256 values, but they're going to range between 31.75 to negative 31.75. So we can store real world values, real numbers, in binary using this system. And this is fixed point representation. But you can see what the problem is. The range is very, very low. So for us to get more flexibility in this type of a restrictive system, we need to move to floating point representation. And to move to floating point representation, we're going to go back to the use of exponents, mantissas, signs, and bases. Now what you see on screen is the typical way a scientific notation is written in denary. A defined number of bits are used for what is called the significand or mantissa. The remaining bits are used for the exponent. The radix or the base is not really stored because the implied value of that is 2, because we're working in binary in this case. So it's assumed that you'll be working with binary representation all the time. If you see something like m times r to the power of e, you should be able to explain that m is the mantissa, e is the exponent, plus minus is the sign, and r is the base. So let's start looking at floating point representation in a bit more depth. Now, the example that you will see is real numbers in 8 bits. So we're going to give 4 bits for the mantissa, 4 for the exponent, and we're going to use 2's complement representations. The exponent itself is stored as a signed integer. The mantissa has to be stored as a fixed point real value. The question now is where the binary point should be. 2 of the options for the mantissa being expressed in 4 bits are shown below. And in each case, the denary equivalent is also shown, and the position of the implied binary point is shown by a gap. Table C shows 3 large magnitude positive and negative values for integer coding that will be used for the exponent. So let's start delving into this a bit more deeper. So table A on the screen shows a first bit pattern for a real value and what the real value will be in denary. So you got 0, 1, 1, 1. So 0 says that the sign is positive, 1, 1 equates to 3, and then the space denotes that the other one is a half because it's 1. So that's 3.5. If you have 0, 1, 1, 0, that's equivalent to 3 because 0, 1, 1 is still 3, positive 3, and the 0 with the on the right hand side of the space denotes that it has no value for the fractional part, so it's 0. We can also look at the negative values there. So the interesting one is to look at what's happening with 1, 0, 1, 0. That's equivalent to minus 3. How is that possible? Well, the first value on the left hand side will be a negative 4 because the sign bit is combined with the value itself. So in this case, you got minus 4. And then you've got a 1. So minus 4 plus 1 equates to minus 3. That's how the fourth value in the table is. Let's look at the next one. 1, 0, 0, space 1. So the one towards the right hand side is obviously 0.5, and the one on the left hand side is minus 4. Minus 4 plus 0.5 gives you minus 3.5. And the last value in table A is 1, 0, 0, 0, which means that 1 is minus 4, and the others don't hold a value, so it stays as minus 4. Now if you look at the second table, table B, which is a second bit pattern for a real value, so here we have 0, and then we can also store 1, 1, 1, which now is on the other side of the fractional part. So what's happening is that we've allocated 1 bit for the integer part and 3 bits for the fractional part. So in this case, you're going to have 0, 1, 1, 1, which equates to a half plus a quarter plus an eighth, which equals to 0.875. You can work the maths out. If you look at the next one, it's 0, 1, 1, 0. That's equivalent to 0.75, half plus a quarter, 0.5 plus 0.25, 0.75. And then you can look at the third one, which equates to 0.625. Now, if you look at the fourth value, which is now quite clearly the negative value, what you're going to have is 1, 0, 1, 0. So the 1 stands for minus 1. Okay? And then 0, 1, 0 equates to 0.25 because a quarter is 0.25. Minus 1 plus 0.25 equates to minus 0.75. And similarly, you can work out the rest of the values. The last value in particular will be 1, 0, 0, 0. That's the easiest to work out. The 1 stands for minus 1, and the fractional part is 0, so the answer is minus 1. Now, as you can see, depending on where we place the binary point or the decimal points, depending on what you're looking at it, binary point if you're working with binary, decimal point if you're working with decimal. Wherever we place that little point, the range of values changes. For example, if we move the point towards the right hand side, that means you're only allowed either half or 0. So you don't have that great a range of fractional values. You might have a greater range of integer values, but a very limited range of fractional values. Now, if you move the decimal points right next to the sign bit, you get a greater range of fractional values like 0.875, 0.75, but a very narrow range of integer values. Now, it can be seen that having the mantissa with the implied binary point immediately following the sign bit produces smaller spacing between the values that can be represented. And this is the preferred option for a floating point representation. Using this option, the most important non-zero values for the floating point representations are shown below. The implied binary point and the mantissa exponent are shown by that gap that we have in there. So a greater range of positive and negative values are available if floating point representation is used. By default, even if you don't see the binary point in a question, it is implied that the binary point is going to be after the sign bit. That means it's going to be immediately after the first bits on the left-hand side. In this case, we've just denoted it with a space. So if you were looking at the largest positive value, 0 is the sign bit, so it's a positive number. 111 is the mantissa part, and 0111 is the exponent part. So the mantissa part, because the decimal point is to the left of it, that's a half plus a quarter plus a eighth, which equals 0.5 plus 0.25 plus 0.125, which equates to 0.875. Now you times it by the base, which is obviously 2 because it's a binary representation, and then you look at the last 4 bits which give you the exponent, which in this case is 0, 1, 1, 1, which equates to 1, 2, 4, and minus 8, because the first one will be the sign bit. So since minus 8 has 0, therefore we just have 4 plus 2 plus 1, which is the equivalent of 7. So 2 to the power of 7, that's how we work out this particular binary representation. Now you might want to pause the video at this particular point and maybe go through the rest of the values, so the smallest positive value, smallest magnitude negative value, largest magnitude negative value. So that should allow you to get a grasp of how floating point representation works. So remember, the binary point is to the left, it's immediately after the sign bit, and the rest you just need to work out by giving the relevant headings. So for the mantissa, you will always end up with a half, a quarter, an eighth, 1/16, 1/32. And for the exponent, you would always go with 1, 2, 4, and the last one is going to be a negative number. Okay. Now we're going to do some examples to get a hold of this. Once you get a hold of this, it's actually going to be pretty easy. There are normally 2 or 3 methods at a time to deal with these type of representations. One might be easier depending on your inclination. If you're an able mathematician, you could just simply work it out. Otherwise, you can just play around with the binary point, and that allows you to arrive to the answer a lot more quicker. So let's look at how this process works. So at AS level, we learned about how binary numbers can be stored in a fixed point representation. That basically means that the representation doesn't change. 8 bits allowed a range of -128 to 127 using 2's complement. This limits the range of numbers and does not allow for fractional values. So how do we go about storing big numbers? Well, let's look at this big number, 312110, and you got another 18 zeros after that. This can also be denoted as 0.31211 times 10 to the power of 24 in scientific notation. But if you wanted to store it normally, you'd end up using 24 bits. But we don't have 24 bits. So how do we go about that? Well, in this case, we could use mantissa and exponent. So the first bit is allocated as the sign bit, and then we can just use 5 bits to store the actual mantissa part, which in this case is 31211, and then we can use the remaining 2 bits to store the exponent part. In this case is 24. 2 times 10, 4 times 1. Now, this is a bit of a cheat really, because I'm just using scientific notation or base 10 notation. In binary notation, we're going to be using base 2, and that means the range of values are going to be a bit more smaller than this, but the principle is exactly the same. You can apply exactly the same technique in binary with a base 2 for exponents. That's basically the essence of floating point representation, to float the binary point in whichever direction to allow us to store a greater range of numbers. Now let's look at what the headings would be in floating point representations. Using 8 bits for mantissa and 8 bits for exponent, with the assumed binary point between -1 and half in the mantissa, so that means immediately after the sign bit, the column headings will be as follows. So the left-hand part is the mantissa, the right-hand part is the exponent. So you start with -1, that's basically where the sign bit is. Then obviously you got the binary point, then you got the half, quarter, eighth, 1/16, 1/32, 1/64, and 1/128. When you look at exponent, you can start from the right-hand side and put in 1, 2, 4, 8, 16, 32, 64, and then the final value will include the sign bit, so it becomes -128. And that's the general principle for the headings. Now let's use these to convert this particular binary floating point number into denary. So the number is 010111010, that's the mantissa, and the exponent is 0000100. So the first step for us is to add the mantissa values. Now you can see that we don't have anything in -1. We got 1/2, we got 1/8, we got 1/16, and 1/64. When you add them up, you get 45/64. Now similarly, you can work out the exponent values. We have nothing in all of the places apart from a 4, so the exponent becomes 4. Now put that into our equation, m times base to the exponent power, or m times r to the power of e, and then you got 45 divided by 64 times 2 to the power of 4, or 45 divided by 64 times 16, which equates to 11.25. Now do pause the video and work this out yourself. In the exam, would you need to work out this using mental arithmetic or written arithmetic? Yes, you will. Calculators are not allowed. So the more familiar you are with using halves and quarters and eighths and 1/16, the better it will be for you. So try to check whether the answer that you see on screen is actually correct. So pause, check, and continue, and we'll move on to method 2. Now imagine if you're not very good at adding fractional values, which quite a few students often aren't, there's another quicker method to work this out. And if you remember the pattern when we were looking at that scientific notation earlier on, what happened when the powers were reduced? So as the powers went down, the decimal point moved to the right. So we're going to be using the same technique. So if the exponent value is positive, we move the binary point a same amount of places to the right. And if the exponent is negative, we move the binary point towards the left. Let's see how this works with our existing example. So we've still got that example 0, 1, 0, 1, 1, 0, 1, 0, and 0, 0, 0, 0, 0, 1, 0, 0 as mantissa and exponent values. So step 1 is to work out the exponent. In this case, we know that the exponent is 4. Now the second step is to write the value down as 0 binary point 1, 0, 1, 1, 0, 1, 0. Now the final step is to move that binary point 4 places to the right. So it now becomes 0, 1, 0, 1, 1, binary point 0, 1, 0. Now put all of that in binary format. So we now basically know that the left-hand side is going to be the integer part, and the right-hand side is going to be the fractional part. So equating that 0, 1, 0, 1, 1 actually becomes 11, and binary point 0, 1, 0 actually becomes a quarter, which means it's 0.25. So it's a quicker way of getting to the same answer as method 1 by simply shifting the binary point a set number of places depending on the exponent. Now it's no fun just looking at or listening to someone doing maths. You've got to try this out yourself. So on screen, you see another binary floating point number. You need to convert this into denary. You may choose to use method 1, you may choose to use method 2. So pause the video and work this out. Okay, so hopefully you've worked out the answer, and the answer should be 2.5. But if you're not sure how that happened, let's try the easy way. Look at the exponent. 2 plus 1 gives you 3, so that means it's a positive 3. We need to move the binary point 3 places to the right. So we move the binary point in between 1/8 and 1/16. Okay? Now we reset all of the headings. So on the left-hand side of the binary point, you get 1, 2, 4, and -8. So quite clearly, that 1, which currently is on a quarter, becomes 2. And on the right-hand side, the 1 becomes a half, which is 0.5. So 2.5. That's how simple it is. Now we can do exactly the same process when converting negative values. So here you see another binary floating point number. We need to convert it into denary. And using method 1, we can use the same kind of technique. So write down all the headings, put the binary floating point values in the right place. We can add the exponent values. In this case, it's 8 plus 4, which is 12. And we can add the mantissa values, which are 1 in -1. So we got to say -1 plus a half plus 1 over 16 plus 1 over 32. Add them all up, you get minus 13 over 32. Using m times 2 to the power of e, we get minus 13 over 32 times 2 to the power of 12, which you then equate down to gives you minus 1664, which is the denary value. Now, it requires a lot of calculations, and this type of example is quite complex. So some of you might need to use the calculator to do it. And these type of questions won't be there in the exam. This is just to illustrate how complex it can get. Normally you get very simple examples to do. But we're going to try doing this same thing using method 2 and then method 3 as well. So in method 2, we're going to work out the exponent first. So 8 plus 4 is 12. And it's a positive number, so we need to move the binary point 12 places to the right. And then we reset all the headings. So what's happening now is that binary point is moving away from the first two ones, and it's going 12 places to the right, and obviously we will keep adding zeros since there's no other values at the end and until we reach the right space. So now you can see we've got headings 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, 5, 1, 12, 1, 0, 2, 4, 2, 0, 4, 8, and the final one is minus 4, 0, 9, 6, because that first value on the left hand side will always be the sign bit. Now, put the values in 1, 1, 0, 0, 1, 1, and the remainders are all zeros. And then on the right hand side of the binary point, since we were adding new values, that's also going to be 0. So now we've got minus 4096 plus 2048 plus 256 plus 128. A lot more simpler to do from the maths front, and that equates to minus 1664. So it's pretty easy to use that floating point mechanism to calculate even complex negative binary floating point numbers. Now there's another method you could apply, which uses 2's complement, and sometimes in exam questions you're asked to use this 2's complement method. So convert this binary floating point number into denary using 2's complement. So the same number that we had previously, which we know the answer should be minus 1664, using 2's complement. How does that work? Well, since the mantissa is negative, we first need to convert the value using 2's complement, right to left. So the first step is to flip the bits. So the original mantissa is 11001100. When we flip the bits, the ones become 0 and the zeros become 1. So we now get 00110011. Because it's got 2's complement, we're going to add 1 to it. So we do that, that's step 2. And this now gives us a new number, which is 00110100. So remember, step 1, flip the bits. So you inverse them, and then you add 1 to it. Now this new number, we can just simply write it down, 00111010. And then since the exponent is 12, which is 8 plus 4, we do exactly the same thing that we did previously. We move the binary point 12 places to the right. But this time around, we've got a new number instead of the original number that we had. So now we've got 001101, and the remainders are all 0. Now, if you equate this one, what happens is you get 1024 plus 5112 plus 128, which also equates to 1664. But this 1664 is currently positive. So the final step in this algorithm is to just restore the sign bit. So if the original one had a negative sign, we just put the sign at the end. So 3 different ways to work out the same answer. You can pick and choose which one you think is the most easiest for you. Now let's work out another example. This time it's over to you. Convert this binary floating point number into denary. Now do pause the video and go through this. It is a bit more complex. You're not going to get anything like this in the exam ever. So try to have a go and perhaps send your answer to me. Okay, that takes care of converting binary floating point numbers into denary. What if we want to convert denary numbers into binary floating point? That's the next step. Now you might want to take a bit of a break before you continue on, because again, a lot of maths can often make us go fuzzy. So take a break, and when you're ready, continue with the remainder of this lesson. Okay, so now we're going to convert 4.5, which is a denary real number, into a binary floating point number. Now there's again multiple methods to do that. We're going to try the more difficult one first, and then we're going to look at the easier version of it. So let's start with 4.5. The first step is to turn the number into an improper fraction, which basically means it's top heavy. So 4.5 is the equivalent of 9 divided by 2. So we keep on dividing it by 2 because we're working with binary. That's the second step. And how many times do you need to divide it by 2? Well, that entirely depends on you. So the idea is that as long as you can get to a decent enough exponent and a decimal equivalent mantissa, you're pretty much okay. So in this particular case, let's just do it about 3 times. So 2 times 2 times 2 is basically 8. Therefore, 9 over 2 can be written as 9 divided by 16 times 2 to the power of 3. And then if we use m times 2 to the power of e, we can then simplify 9 over 16, which is the same as a half plus 1 over 16. And you can try these combinations yourself. You can try to work it out and convert 9 over 16 into a binary representation, which should work out to 0.1001. So you got a half, and then you got 1 over 16 at the end. So the idea is to simplify this improper fraction into the binary equivalent of decimal point headings, so half, a quarter, an eighth, and a 16. Once we have all of that, then we can just simply place these values into the relevant 8-bit notation. So 9 over 16 is pretty straightforward, 0, 1, 0, 0, 1, and the remaining bits are zeros, and 3 just equates to all zeros and the last 2 digits as 1. And that's all it is. But this one does require a bit of thinking, a bit of calculation. You need to be comfortable with your fractions, and you should be able to learn how to divide by 2. And if you are, this is pretty easy. You would understand this. However, the second method is actually a lot more simpler. So those of you that might not be as mathematically inclined, this might actually work out a bit better. So what we're going to do is first, we're going to split the 4.5 into 2 parts. The 4 is the integer part, so we just simply convert it to binary, 0, 1, 0, 0. And the 0.5 is equal to a half, so that is equal to dot 1 in binary, or binary 0.1. Now when we put these together, we get 0, 1, 0, 0, dot 1. Now floating point representation expects the binary point to be right after the sign bit. Therefore, this binary point needs to move 3 places to the left, so it comes after the first 0. So 0, 1, 0, 0 binary point 1 becomes 0 binary point 1, 0, 0, 1 by moving the binary point 3 places to the left. So the exponent in this case must increase by 3. So you can see what's happening here. We end up with the same answer. Now, since we've got 3, which is equivalent to 1, 1, we can just place these values in the relevant mantissa and exponent 8-bit notation. So 0, 1, 0, 0, 1, 0, 0, 0, and 0, 0, 0, 0, 0, 0, 1, 1. We arrive to the same answer as method 1. Hopefully that was clear. I particularly find this a lot more easier and a lot more quicker to work out the notation of a real number into floating point binary representation. Okay, so how do we go about converting negative values into binary floating point number? Now this can be a bit tricky. However, the method is exactly the same. But since it's a negative number, the easiest way is to use 2's complement. So let's look at converting minus 4.5 into a binary floating point number. So we're going to do minus 4, which we convert to 4, or we just put the minus sign in front of it. So 0, 1, 0, 0 is basically 4. The minus sign stays where it is. And 0.5 is equal to a half, which is equal to 0.1 in binary. So put these together, we get minus 0, 1, 0, 0, 0.1. Now that part is pretty straightforward. However, since this is a negative number, we need to use 2's complement to convert it back. So we flip the bits, so the zeros become 1 and the 1's become 0. So instead of 0, 1, 0, 0, dot 1, we now have 1, 0, 1, 1, dot 0. And in this process, we end up losing the negative or minus sign. We also need to add 1 to complete the process. So we now have a new number, 1011, dot 1. Now what you're going to do is shift the binary point next to the sign bit. So in order to make 1.0111, it has to be moved 3 places to the left. And that means the exponent is 3. So your mantissa becomes 10111,000. We fill the remainder of the spaces with 0. And the exponent is therefore 3. If you want to check your answer, you can then try to resolve this binary floating point number back to denary using the techniques you know, and it should give you minus 4.5. Now, it's all well and good talking about maths, but as usual, you've got to do something to understand it. So on screen, you have a couple of real numbers which you need to convert into binary floating point numbers. You might want to try method 1 if you're brave, or you might want to use method 2. Whichever method you use, try to solve this and then share your answers with me. Here's another question for you. Show why the first set of numbers are the same as the second set of numbers. So both numbers are in floating point binary representation. You might need to decode these numbers into real numbers and then work out how they are similar. So once you work it out, share your answer with me. And finally, on screen, just because you are now comfortable, hopefully, with conversion of real numbers into binary floating point and vice versa, here are a few more questions for you to just get your teeth into. Pause the video and have a go at these. Okay, that's enough working out. Here's another challenge for you. Can you code a floating point calculator in Python? You should have picked up that all of these are basically steps or algorithms. And because these are algorithms and you've got to do a few things like step 1 do this, step 2 do this, you can actually code it. You can actually create a floating point calculator where you can type in a real number and it should give you the appropriate binary floating point number as an answer. And you might want to do the same thing. Put in a mantissa, put in an exponent, and it should give you the real number as an output. Now try to limit it to perhaps 8-bit mantissa and 8-bit exponent because they might be easier for you to calculate, or even if you want to simplify it, go a bit further down to 4-bit mantissa and 4-bit exponents. That might just be the limit. Remember, you can expand this calculator if you so wish to bigger binary digits once you work out what the pattern is. However, this is a nice challenge for you to try, especially in Python. The link or the description of the link on screen will give you a hint on how to code this. So if you get stuck and you can't think of a way out, you might want to go to this particular website and learn a bit more about creating this type of calculator. Okay, that brings us to the end of a very long lesson. You should know by now what are the two components of a binary floating point representation. You should also be able to explain how you would convert negative binary floating point to denary. And in addition to that, how to convert denary numbers, both positive and negative, back into binary floating points. That's all for today. And in the next lesson, we'll wrap up this particular unit before we start moving on to Unit 14, which is all to do with communication and protocols. I'll see you in the next one.